Every morning, the sun sends an unimaginable amount of energy towards the earth. In just 1 hour, enough sunlight reaches our planet to power human civilization for an entire year. Yet, for most of history, that energy simply passed us by. Today, we do something remarkable. We capture light and turn it into electricity. But how exactly does this happen? Well, everything begins with one extraordinary phenomenon, the photovoltaic effect. Unlike burning coal, splitting atoms, or spinning giant turbines, solar electricity has no moving parts, no flames, no smoke, no fuel. Instead, electricity is produced when tiny packets of light called photons strike a specially engineered material. When enough of these photons arrive, they transfer their energy to electrons trapped inside the material. Those electrons begin to move, and moving electrons are electricity. It sounds almost magical, but it's pure physics. Not every material can perform this feat. Scientists search for materials that can absorb sunlight while allowing electrons to move freely. And one material stood above all others: silicon. Silicon makes up roughly a quarter of the Earth's crust, making it one of the most abundant elements on the planet. And it can be found in ordinary sand, quartz, and rocks. More importantly, silicon possesses a nearly ideal bandgap, an energy threshold that matches most of the sun's visible spectrum. If the bandgap is too small, the energy is wasted. If it's too large, energy passes straight through. Silicon strikes an exceptional balance, converting a useful portion of sunlight into electrical energy, while remaining durable, stable, and relatively inexpensive to manufacture. This combination of abundance, performance, and manufacturability made silicon the foundation of the modern solar industry. Today, more than 90% of solar modules worldwide are built using silicon. A silicon solar cell may appear simple, but beneath its surface lies careful engineering. Pure silicon itself does not produce electricity efficiently. To unlock its potential, engineers create two slightly different forms of silicon. One type contains an excess of electrons. This is called N-type silicon. The other side contains spaces where electrons can move into. These empty spaces are known as holes, creating P-type silicon. Now, when these two materials meet, they form what engineers call a p-n junction. This microscopic boundary becomes the heart of every solar cell. At the junction, invisible fields naturally form. Think of it as a one-way street for electrical charges. Now, when sunlight arrives, a photon enters the silicon crystal. If it carries enough energy to overcome silicon's bandgap, it knocks an electron free from its atomic bond. But something else is left behind, a hole. Together, they are called an electron-hole pair. Left alone, the electron will simply fall back into the hole. No electricity will be produced, but the electric field inside the p-n junction acts immediately. It pulls electrons towards one side and the holes towards the other, and the charges are separated before they can recombine. If you connect an external wire, the electrons now have somewhere to go. They travel through the circuit, powering lights, computers, motors, homes, and entire cities. This continuous movement of electrons is direct current, or DC electricity. Every single solar panel on Earth operates using this elegant process. A single solar cell produces only a small amount of electricity. To generate meaningful power, many cells are connected together. These become a solar module, commonly known as a solar panel, and each layer serves a specific purpose. The front glass protects the cells from weather while allowing sunlight to pass through. A transparent encapsulant cushions and seals the delicate cells, protecting them from moisture and mechanical stress. The silicon cells harvest the sunlight. Behind them lies another protective layer called the backsheet, which provides electrical insulation and shields the module from the environment. Around the edges, a lightweight aluminum frame gives the module strength and allows it to be mounted securely. Finally, on the rear, the junction box collects the electrical output and connects the module to the rest of the solar system. Each layer has one purpose: to protect the fragile photovoltaic cells while allowing them to harvest sunlight for decades. Many of today's modules are designed to continue producing electricity for over 30 years or more. The science behind solar energy is astonishingly simple. Light arrives, electrons move, and electricity flows. By transforming this elegant principle into one of the world's fastest growing technologies took nearly 2 centuries of scientific discovery, engineering, and relentless innovation. The story of solar power is only just beginning. I've been Jason. I'll see you on the next one.